Welcome back, everyone, to what is, I guess, the last lecture of actual content for this course. And the lecture after this is going to be about exam review. So this is the last stuff that will be covered on the exam. And I'm giving this lecture virtually from a hotel room. So we'll see how this goes. So I guess feel free to ask questions on the chat instead of in person now. Or I guess if you want to ask, you can ask in person as well. And then Ali Reza, or maybe I'll hear you and I can answer them. So anyways, let's remind ourselves what we were kind of doing last time, which was this neural network stuff. And so we're going to spend like the first kind of 5 to 10 minutes wrapping up this neural network section. And then the lecture for today is going to be about language models, which is the last kind of chapter for the course. Okay, hopefully the fire truck isn't super loud in the background. But okay, so we were studying these neural networks. And what we saw is that this neural network is just a function. And it has some special structure, and we've seen all sorts of functions in this course. We've seen like these linear functions and the sigmoid applied to a linear function. And so we should think of the neural network as just like some other function where visually it's represented like this, where there's an input here. And then it's a directed graph that moves to the right, and really these should be like directed edges. And information flows from left to right until you reach this output kind of neuron here. Okay, and then we saw that ultimately, everything that we've learned in this class stays the same. The only thing that's changed is the set of functions that we're using for predictors are now changed to neural networks. And so this ERM algorithm that we've been using throughout the course is exactly the same, except the function class has now been changed to be functions that map from features to labels, but the function is now a neural network. Okay. And then we went through a bunch of details of how neural networks are a generalization of many of the functions we've seen, such as the linear function, which you can draw as a neural network like this, and the sigmoid applied to a linear function, which you can also draw in the same way, except the non-linear activation function for A should be chosen, this H should be chosen as the sigmoid. And then after that, we moved on to see why would neural networks kind of be interesting. And the idea was something like, well, you know, maybe your features are kind of not expressive enough to begin with. So then we've seen in this course that you can map them in a kind of user-defined way. So you might choose to map them through this like polynomial function. But this choice might be kind of wasteful in the sense that you may end up mapping to all sorts of features that you don't actually need to represent the corresponding function of interest. And so many of the new features in this polynomial map can be wasteful or not very useful. And in particular, when the polynomial degree is very large. And so the kind of story here is that, well, a neural network will hopefully kind of learn which features are important. And the way we saw this before is that if you train a neural network, and by train this means like run ERM using, let's say, gradient descent, and then if you look at the neural network's activation, so the value of these neurons when it's already been trained, this would be the output of your learner. Well, then what you would notice is kind of these internal activations are largest for certain types of inputs, and these certain types of inputs can be interpreted as like the features they learn. And so some examples for like classifying whether something is a cat or not can be thought of as follows. You input the raw pixel values, and then as you move through the network, what you notice is that like in the first layer, and this is kind of stuff that has been empirically observed by researchers, in the first layer you might notice that this activation is the largest when maybe like this edge is kind of active. And so that would mean like maybe it's kind of tracking the edge that's the back of the cat. And maybe this neuron is the largest when it kind of spots the back feet of the cat. And then as you move deeper through the network, you find that these kind of activations are largest for more complex kind of characteristics, such as maybe the head of the cat or kind of the torso. And if you add more layers, then you can break this up into even more kind of complicated behavior. Okay. And then we moved on to mathematically defining how this neural network worked, and that we are just going to kind of skim over and say that, well, there is some way of doing this, and then you can review the last lecture to see how that happened. But the general idea is that the neural network has a few things you need to define, and then you have yourself kind of a neural network. And those things were the number of layers, which was b, and that can be chosen to be whatever you want. And then the number of neurons in each layer, so how many neurons you have in a layer, that was like this d to the power of layer number. So each layer can have different number of neurons. That's an important other kind of parameter to describe a network. Another thing was the activation function that is used at each layer. So that was this h function. There was this activation. And if you define those three things, which is the number of layers, the number of neurons in each layer, and the activation functions you're using, you get what is called like a neural network architecture. And so you have like basically kind of the structure of the neural network defined now. And all that is left is what is the value of the weight on each of these connections. So what are the weights? So the only thing that's missing is the value of the weights. And that is going to be kind of the parameter or the set of weights that define a neural network after you fix the architecture. And that's going to be what we're searching over. Okay. And so when we get to this ERM learner, the function class we have is the set of neural networks with some specific architecture you choose beforehand. Okay, so you pick your architecture, which once again just means you pick the number of layers, the number of neurons per layer, and the activation function. And then all that's left is to define these weights. So each function in the function class can now be described by just a set of weights, which is just a bunch of real numbers. And the beautiful thing about that is that if we then run ERM, what you need to do is minimize over this type of functions. And that is equivalent to minimizing over these weights, which is just a very large kind of dimensional real number, is what you should think of. And we've seen throughout this course how to minimize such things. So if you have a minimization problem over a giant vector of real numbers, well, then you can run, for instance, gradient descent. And so in this course, we don't actually end up using, or you don't end up like calculating the derivatives and like the gradients for this. But the procedure to do this is commonly referred to as backpropagation. And you've probably heard this word if you learned or heard anything about neural networks, and that's really just the procedure to calculate the gradients of the estimated loss, where you use the predictor as a neural network. And it's kind of complicated because there's a lot of layers and you have to do a bunch of chain rule steps. And yeah, it has a special name. And in this course, we don't cover it, but in, I guess, like 4, 6, 7, you do go through those steps. And it's just some math. Okay. And the reason we use gradient descent is that there's usually no closed form solution unless you pick a very simple neural network, like maybe the linear functions, the specific neural network, which is linear or something like that, then maybe things will be okay. And in general, also, unfortunately, this estimated loss is usually not a convex function. And so also, this is where we kind of ended this course about how to deal with this, but what that means is you will not actually find like the global minimum, but you would find this like local minimum sometimes. And that is also kind of a topic for future courses. And obviously a big kind of issue with neural networks compared to the other function classes we've studied. Okay, great. So all that was left to discuss about neural networks before we move on to language models is going to be this idea of how to implement the softmax. Because notice we've kind of covered this like linear functions, then we covered this sigmoid applied to a linear function, which we use for binary classification. And then for multi-class classification, the usual function you would use there is the softmax of the linear functions. And I just wanted to kind of like give you an idea how this maps to neural network land. So let's just remind ourselves how the softmax works. So if you had like 3 dimensions and you had 3 classes, so now that we're in the multi-class classification setting, well, then the softmax was this kind of function that gives you a probability of each class. And so we had like the softmax of the first class. So this was a function of these three values. So these were like numbers between possibly negative and positive infinity. So remember these guys here, they're a real number. And you wanted to map them to kind of a number between 0 and 1 that summed up to 1. And so what you did is you applied the softmax to these three numbers, and then it would kind of normalize it to a number between 0 and 1, such that it also summed up to 1. And so this number here is the probability you get of the first class, this is the probability of the second class, and this is the probability of the third class. Okay. But the critical thing to note is that to do this normalization and to ensure that it sums up to 1, you really kind of need to know all of the three values, the three predictions. And this is kind of not super easy to do in a neural network with just one layer, let's say. And so if you try to do this in a neural network with one layer, what you'll find is that, well, this kind of activation here can only depend on these previous values. And so its value looks like this. And so you notice that, unfortunately, it only depends on like the input times the like one weight vector. And then this activation will depend on the input times its weight vector. And for the softmax, you somehow want to have a function that depends on all three weight vectors. And so it turns out that like you can't implement softmax with a single layer neural network. So softmax cannot be implemented by a single layer neural network, at least in the kind of way we've studied neural networks, the way the connections work. And so this gives you two options, which is to add more layers to kind of implement this softmax stuff, but that's kind of ugly and people usually don't do that. So what they do is essentially what happens is you just decide to add what is like a kind of a post-processing step at the very end of the network, which just allows you to kind of take as input all of these neurons and then just normalize by them. And this is commonly kind of what is done. So instead, you should think of how like when you apply a softmax on a neural network to look something like this, which is your neural network will, at its outputs, just produce the pre-activations. And then the softmax will just take those pre-activations and then apply the softmax function and produce each corresponding class's probability. Okay, and this happens kind of a lot, as we'll see, because you can change everything on the left to be a very big neural network. And then you can get some real values at the end, which will be like your final activations of neurons. And then what you will do is like you'll add this final post-processing step, which is the softmax, to ensure that all of these numbers sum to 1 and are themselves values between 0 and 1. Okay, and we'll see this today, and that's why it was kind of, we're mentioning it now. So this, you should think of this once again as kind of like a post-processing step that allows you to map all of your kind of your three final values into a probability kind of mass function, something like this. Okay, and so finally, before we move on to language models, I just wanted to make a couple notes about like, I guess, high-level things and how this relates to the real world and things like this that you may hear in the wild. And so here are the notes. So companies end up releasing models, and models is like the final neural network. So they would release a neural network. They would tell you like, so if we look at a picture of a neural network, they would release a neural network. And the question is like, what information do they tell you? So this has already been trained. So the weights have all been set and so on. And there's kind of two ways that companies release stuff. And there's like a closed source and an open source release. Okay. So people call this like black box access. So companies they won't even tell you the architecture and they won't tell you the weights. And so they'll only allow you to pass in an input and then get the output. And so you have no idea what's going on the inside. However, it is some neural network behind the scenes. And so examples of these are like language models such as like ChatGPT, Gemini, and Claude. And so these, the only access you have to them is through an input, and then they produce your output, and you have no idea what's going on inside it. And then there's other companies or language models, for instance, that give you open source releases. So that means they'll actually tell you the architecture and the weights. And you can further change the weights if you want and stuff like this. And examples of this are like Llama, which is by Meta, and Gemma, which is by Google, DeepMind, which is like their smaller version of their language models, which are open source. Okay, so that's the thing to know. Also in this class so far, and from now on, like in the next lecture, we studied a special type of neural network called like a multi-layer perceptron. So it has this very special way of connecting between the layers and so on. But people have come up with all sorts of different ways to like connect weights between layers and add like skipping connections between layers and so on. And there's all sorts of different types of neural networks, and they have other names. So some examples are like a CNN, which stands for convolutional neural network, which people use for usually for vision, which is like image classification stuff. Another example is the RNN. Oh, apparently someone's vacuuming beside me. Okay, anyways, there's an RNN architecture, which is like used for language model stuff in the past, and now the most kind of common current one is the transformer, which is used for language modeling. And for instance, GPT actually stands for generative pre-trained transformer. So ChatGPT and many of these language models behind the scenes are using kind of these transformer neural networks. And we will not go into how that architecture looks, but it is just kind of a modification to the neural network architecture we've seen where the weights and stuff are connected in different ways between layers. And people also talk about this terminology called deep learning. And deep learning just refers to basically using neural networks as your function class, but having B, the number of layers, to be very large. And that is what deep means for deep learning. So usually the number of layers is referred to as the depth of your neural network. And so if you have a very large depth, a very large number of layers, then you have deep learning. Okay, so that's everything I had to say about neural networks. Let's jump into now language models. And there we will be using neural networks as well. And we'll see how kind of everything we've learned in this course will set us up to almost immediately understand how the current kind of language models are being used. Okay, so is there any maybe questions about anything else before we start on that? Is there a question? I hear someone talking. I don't hear them, but I hear them very quietly. Okay, well, I'm going to assume that I can just continue. Okay, so yeah, topic for today is this language model stuff. And the kind of task we're going to be caring about is a generating text. And we'll talk about what kind of text we want to generate and why in a second. But we can think of some examples, just like kind of an idea of what generating text might look like. Well, an example of like generating text is like you should think of like you have some input. And you should think of this like so far we've been studying, this very specific kind of case where you had these inputs, which are feature vectors, and you output like a label, which was a number, or maybe like a class or something. Well, now your input's going to be like, let's say, some English sentence, and then your output's going to be an English sentence as well. Okay, like let's see some examples. So maybe you inputs the beginning of some sentence, like once upon a time in a land far away. And then maybe the output you would expect is like to finish the sentence, which is like there lived a wise old dragon who loved to read books. Maybe that's one possible continuation of the sentence. And there's many others, of course. Okay, another example is like you might input a question and then hope for a response to be like a kind of an answer to the question. So the question we're gonna use throughout this lecture as an example is the question, why did the chicken cross the road? So kind of remember that question. We'll see it a lot. And maybe the answer, the kind of correct answer maybe is the classic response, which is to get to the other side. Okay, and maybe you would hope for something like to have some sort of model, let's say, that takes in input sentences and outputs like correct responses, something like this. Okay. And so before getting into too many details, like roughly speaking, the way ChatGPT works is you really do input, I mean, as you interact with it, you input a sentence and or like a question usually, and it'll produce some sort of answer and somehow decides how long the answer should be and whether it's a good one or not, but it outputs an answer for you and you see that. And one thing I wanted to mention is that like behind the scenes, the way this actually works is there's this extra part, which is this thing, that gets appended to your input, which is called like the system prompt. And you never see this, but companies, like each of the big language model companies, do this. And what it really does is it kind of tells, I guess, the language model at the very beginning what it is or what it's expected to do. And so they'll append this thing like, you are an AI assistant trained to provide accurate, concise, and helpful responses to user inquiries. This was like, I think, a system prompt for like Claude like 3 years ago or 2 years ago or something like that. And then they add much more nowadays, I think, with all sorts of other things that they maybe don't want it to do or wanted to do and so on. Okay, so and that's how it's kind of told that it's this helpful assistant. And after that, this is your input. So this is the user's input. And yeah, so this is you put in your input, which is like the question, and then this is what you will see from ChatGPT as the output. Okay, and then there's a question online which says, if we're doing local inference, do we control what gets put in the system prompt? And I don't know what is meant by local inference, but if you yourself have like access to the input-output behavior of the model, like for instance, I think with like the API access to ChatGPT, you can indeed add like your own system prompt and stuff like this. But the like user, the GUI that you interact with like online, if you type in ChatGPT, they'll have this kind of hidden system prompt behind the scenes. But if you yourself had like the model, then you can of course control what is the system prompt. And if you wanted to make like a product for users, you could make this something different. And if it's like some helpful assistant for math, you would tell it that you're like an AI assistant made for math specifically, and so on and so on. Yeah, and so I guess, yeah, exactly as the follow-up question is, yes, if you locally load the model, then you have access to the system prompt. Or like you can put it in yourself. It's not there for you. Okay, so the question is, how do you kind of create a model that does this for you? Because there's a lot of sentences, right? They're like the input space is massive. It's words, it's text. It's kind of weird. It's discrete. We've been dealing with these continuous like d-dimensional vectors. And also the output is like a massive number of sentences. They can be arbitrarily long, and that's like a lot of possible classes if you think about it. It's like this classification setting. So the kind of way to solve some of this is what is called like autoregressive modeling. At least this solves the part of the fact of like there's a massive amount of outputs that could exist. And the autoregressive part is how kind of like ChatGPT, Gemini, and Claude probably, almost certainly, currently do their language model generation stuff. Definitely was like this a year ago, and it's like very unlikely that they're using something different. Okay, and all this autoregressive stuff means is that what you'll do is you generate your outputs sequentially by using the previous outputs and inputs you've already generated. So this is like this, you're regressing on your own outputs from before. And what this looks like is the following, which is one way to generate an output is to just generate one word at a time. And that's exactly what happens. Okay. So in that way, there's only, all you have to do is just, produce one possible word. So you just have like your vocabulary, which is like all possible words you're going to generate, and you're going to generate each of them one at a time. And so that'll look like this. So for that, why did the chicken cross the road example, what would actually happen behind the scenes when you interact with these language models like ChatGPT is this is what happens. You input, why did the chicken cross the road? It'll then output just one word. So maybe if it's correct, let's say, it outputs 2. And then it will, to its input for the next time, as it's generating, it'll actually add the word to its input. So its new input will be the following, which it adds it appends to the input. And then it'll produce the next word, which is get. And then it'll be like, okay, let me add this to my input. So I'll put it here. And that's what its next input looks like. It has appended both these. And then maybe it'll output to get 2. Okay, and then it will continue onwards until finally it gets to the very end, where it will have hopefully produced why did chicken cross the road. It'll produce to get to the other side. And then it has this special token, which is called the end of sequence token, which it outputs to say, I'm done generating. Okay, so it just generates one word at a time until finally, when it thinks it's done, it's going to output this end of sequence token, signifying that it's done. And then the user will see everything up to the end of sequence token. So this would be the response. Okay, so this is like the autoregressive generation. So given that this is the behavior we're going to study, all that's left is to kind of discuss how are we going to, given some sentence, how do we output a single word? And in particular, kind of how do we output the expected next word? Okay. And then I'll read this question. Someone says, can we constrain the generation for the output using a finite state machine? I don't quite know what that's referring to in terms of what it means to constrain the output. So in this autoregressive way, we'll see that the output is going to be, you're going to be allowed to output any, let's say, English word. And I don't know what the finite state machine has to do with this, but maybe you can elaborate in the chat. But anyways, let's continue in the meantime. Okay, so what we got to is that we essentially want some way to, given an input, some set of like words, we want to produce a single next word. Okay, and so that's going to be kind of our objective. So let me write that down. So we want, and now we're going to use the common terminology instead of predictor. This is really a predictor, but I'm going to use the common terminology, which is we want a model. Right? We want a model, which is, as we've been seeing many times, which is some function that maps inputs to outputs. Okay, and maybe I'll take the question. Yeah. Yeah.
Yeah, sorry, I just want to make sure we are not frozen. What the slides are you talking about right now? Is it autoregressive in the middle of the page?
No, so I'm writing text now. Can you see my screen move around?
Yes, but I'm afraid we are frozen. So if you're changing your slides, we are not keep tracking of that. So the slide that I'm seeing right now has the autoregressive in the middle of the page. Is it the page you're on at?
No, I'm technically on the next page, but
okay. Now it became now it became we want the model F from X to Y.
Yeah, interesting. I think on Google Meet it should be
So we are
okay.
up there.
Okay. Okay.
No, the internet is pretty unstable on my end. Sorry about that.
Okay. Yeah, I think ultimately on Google Meets it is okay. So the recording should be fine in case you missed it in class live. But thank you.
Okay. I guess we're good now.
Okay, cool. Okay, it seems like people online are saying they can see the correct page. Yeah, so anyways, so we're in this state where we want some way to take an input, which is like this sequence of words, and produce a single next word. Okay, and let me just make this a little bit clear. So like somehow from this set, X, our domain, if we took some like X, which I'm gonna write like this, like if we take some X from here, this is like in English, it's just a sequence. This is a sequence of words. And the output of this function, so like f of x, that'll be a label y. So notice where like it's exactly the notation we've been seeing in this class is just the next word. Is the next word. Okay. And so the question is like, what is the set of words we're going to consider? What is the set of labels? And we'll define X in a moment too. And you might start with being like, okay, so this is just like some set of objects, right? And what should we put in the set? Well, maybe we should put all English words, or maybe all words in all language, but let's just stick to all English words for now. So I'll just put that as all words. But then you see that we quickly run into some like weird issues, which is that you're missing punctuation, for instance, and you're missing spaces, and things like this. So you probably don't want to just consider words. You probably want to add like punctuation. And we also needed some way to, say when we're done. That was that end of sequence token. So we probably want to add the end of sequence token as well, which may have not been that's not really an English word. And it's going to turn out that we're going to want to add one more thing to our vocabulary, which we'll see why next, which is like this pad token, which we will use occasionally as well. Okay, and it's going to be kind of a set of things. And this should be kind of sufficient for all of our output needs. And this is sometimes called like your vocabulary. Wow, vocabulary. And so we're going to actually change this terminology from words to what is often referred to as tokens. So now, because these are not just words, they're like multiple type of symbols. The people in large language model world or in language world, they call these tokens. So it's going to be a sequence of tokens. And your output is going to be just a single token. And then you may have heard this very classic terminology, which is that these language models, all they're doing is just doing next token generation. So they're just generating the next token and then appending its output to the previous input and then doing next token generation over and over and over again, and really producing the outputs you see when you interact with them. Okay. To make this kind of easier to work with mathematically, as we've been doing in this class, remember, you could think of this as like a bunch of different labels or a bunch of different classes. And we've seen this before with like, maybe classifying pictures. So here you might have had a set of, let's say, cats, dogs, elephants, giraffes, or something like this. Well, now we have these other discrete objects, which are words, punctuation, and things like this. And so similarly, there's some finite number of them. And so the number of them we will use, so let's say there's k, so let's say the cardinality, which is the number of classes in here, is capital K. Well, then to refer to them, to make things easier and to map to all the notation we've seen before mathematically, we're going to refer to them as classes 1 up to k. And in the past, we indexed from 0 and we went to k minus 1. And now I'm going to go from 1 to k. And I don't really remember why I did this, but it's just a notational remark. So yeah, and it's totally fine to use 0 to k minus 1 here. It's just, I think notationally it was nicer a bit later on when we get places if you do this. Okay, so that's great. And then the input, so hopefully that makes sense. This is just your set of tokens, and you're just going to describe every token. If there's, let's say, I don't know, like 50,000 words in the English alphabet or something like this, you're going to describe each one of those 50,000 words by just a number from 1 to 50,000. So you end up doing what looks like now a multi-class classification problem, where you need to output which class or which token do you think is the correct next output. And that will be some just equivalent to outputting a number between 1 and k. And this set X, which is the sequences, so there's a lot of sequences, because they can be of like any possible length technically. And so we're going to kind of, well, I'll get to it later. But you can see that these sequences are sequences of tokens. So it could be just like a 1 token input, or it could be, 2 tokens as your input sequence, or 3 tokens, or 4. And there's a lot of those. So we'll see how we kind of handle this in a moment. But that's, of course, just made up of tokens as well. Okay. And similar to kind of how we did classification before, we saw that like predicting discrete things is kind of problematic. And so instead we kind of resorted to predicting continuous things, which was like the probabilities. And if you remember, the way we did classification for multi-class was like we predicted the probability of each class. We used that softmax function actually to do this. And then we just chose the class that had the largest probability. And that would be our output. And that's exactly what happens in large language model world, which is that you're going to predict the probability of each class. And then the class you output, the token you output. So you're going to predict the probability of each token. You're going to output the token with the largest probability. So it's the most likely next token is going to be what we're going to do. Okay, so we're going to kind of change our objective. And we're going to say we don't want, I'll just take this. Okay, and maybe I just put one little word here, which is like discrete labels, which is what we have right now, make optimization hard. And so we're going to optimize over continuous labels, which is how we did classification to begin with in this class. And so instead, we're going to want not a model from like X to these labels Y, but instead we're going to want a model from X to a new set of labels called Y prob. And Y probability is going to be this giant vector of probability. So it's going to be like numbers between 0 and 1. Maybe I should write that this is equal to numbers between 0 and 1. And there's going to be k of them, which is the number of tokens. So for each token, this is the probability of that token. We've seen this. This is a giant vector of k numbers representing the probabilities of each token. So this is exactly what we did in multi-class classification. And I'm going to call this now a model, the probability model. And this is really what happens behind the scenes, right? Is you actually end up learning a probability model. And once you have this probability model, you can then select the next token by just picking, let's say, the most probable one. And you can do other things, which we'll talk about at the end. And so now X is the same thing as before, which is a sequence of tokens. But Y is no longer the next token, but it's this thing in this probability vector, which is a vector, right? It's this k-dimensional vector. It's a vector of probabilities. Maybe I should put a vector of k probability values, right? K being the number of tokens. And now this is not F, but F probability. So you're going to learn this probability model. Okay, great. Now I can answer the question, which is, gets related to finite state machines, which is saying, I'm not sure how to describe it, but instead of all words, I think what I'm asking is during generation, can we use a finite state machine to reduce some of the words to have minus infinity to restrict the output to ones allowed by the current state and valid transitions? Right. So I guess the question is something like, based on the current sentence, like there's maybe only some very small set of valid words, so you don't have to consider all those. But I guess my answer is I don't know of any way that people are doing this in a nice, easy way, because I guess some of the problem would be that to decide what are the kind of valid words given your current sentence that you're trying to predict the next word for is itself would be like kind of a challenging problem. It's almost like you need to predict which words should you even consider, in which case you're kind of solving the original problem, which is the best answer I have. Okay. Cool. So yeah, let's continue with how this will look. And it'll look actually, so I already have drawn this picture. So there's going to be a few more pictures coming up now. And I guess these notes are live on the website so that you can follow along with the pictures. And then the idea is kind of like this now, which is we just need to predict probabilities of all these next tokens. And we've already seen how we're going to do this. We're going to apply a softmax, right? And the way the softmax works is for its input, it just needs k real numbers. And before, though, the way we got these k real numbers, which is the number of tokens, real numbers, is we just use linear functions. But now we know about neural networks. And we saw the neural networks are more powerful, and it turns out this is what people use in practice. So that's what we're going to use here. And so instead of using a linear function to produce these z's that then go into the softmax, which is how we saw multi-class classification being done, we're going to add a more complicated kind of way to produce these, which is we're going to add a neural network before. Okay, so the procedure is to be thought of as follows, which is that we're going to use a neural network, so this like F neural network, to produce numbers basically at its output, which is going to be these z's. This is going to be the pre-activations. Okay, so we're going to define the activation at the very end to be the identity. And so the identity will mean that the pre-activation gets mapped to the actual activation value at the end of the neural network. And so the neural network will have k outputs, so the number of neurons at the final layer is going to be k. So in other words, I can put this here, which is the neural network will be such that, and I'll put this here with number of neurons, remember use D, and then at which layer? At capital B, so the final layer is equal to K. Okay, so a neural network with this many neurons at its output, and the identity activation function. So this just produces K real numbers. Will then be mapped to the softmax, which will then convert these into K numbers that all sum to 1 and are between 0 and 1. So in particular, just to remind you, if you take the sum from, let's say, Q equal 1 to capital K, of all these alphas, which are the outputs of the softmax, the property is that they will sum to 1, and each of these alpha Qs is between 0 and 1. So you can think of them as representing the probabilities of the particular token Q. Okay. And yeah, so that's what happens. And so our goal at the end of like what we were doing was we were trying to get this probability function, which took as input some sequence and produced a giant vector of probabilities. And we have actually achieved that. And so this blue box is going to be called fprob. That's going to be our probability function. How does it work? Well, we can see here, it takes in as input some x. It's maybe I shouldn't have put a vector here because we don't understand how this is a vector at all yet. So far, this is just a sequence of tokens. So it's going to take in an x, which is your sequence of tokens. And for its output, it's going to take that x, map it through the neural network, right? And then pass that through the softmax. So it's going to pass this vector of k real numbers into the softmax, and then this will produce the desired kind of probabilities. Okay, so we got our probability function, and you can now see that, like, really what we're going to try to do is try to learn the best possible probability function, such that these kind of like match, you know, the real world next tokens you would see in something like this. And that's going to really reduce to learning the weights for this neural network, because that's the only thing that needs to be learned. Those are the only connections that are unknown. And we're almost there, but the one thing that's kind of missing is the fact that this input is still a sequence of tokens. And so how are we going to reduce the sequence of tokens to what we have studied so far, which is what we studied so far is just vectors in d dimensions, right? That's how our inputs always looked. But we have a sequence of tokens. So let's fix that problem now. So the question is, how do we represent a sequence of tokens, S? And yeah, so this is going to be, and I really should have, okay, so this was like, let me say this. So let's suppose this was really a vector, and this went into here. And this was really a vector. And, okay, well, maybe not. So I'll remove this, and let me just see how I want to fix this notation. Okay, well, I'll just keep it the way it was before. But so if we had this x like this, the issue is that the neural network really expects this to be a vector, right? A d-dimensional vector. That's how we've always worked in this class, because it's going to multiply them. But okay. But at the end of the day, what we're working with is that these are sequence of tokens. So I'm going to use S now to represent the sequence of tokens instead of X. And what we want is we want to represent it as this vector. Okay, this d plus one dimensional vector. So how do we achieve this? This is because this is how we've dealt with everything in the course, and that's all we kind of end up knowing how to represent functions of is like these vectors, because then we can multiply it by weight vectors, which we can optimize over. Well, the way this is going to work is as follows. First, let's just kind of understand what the sequence of tokens looks like. Right, our inputs will look like this, which will be like some token v1 up to some token vc. So let's say this is some input that has c tokens. So for example, if the input was why did the chicken, then your sequence of tokens would look like S, which is this token appended with this, and this. This has 4 tokens. So this would be an element of, token space to the power of 4. And so then C would have been 4 here. Okay. So what are we going to do to solve this problem? Well, it turns out it's actually quite a reasonable idea, and this was maybe not so obvious quite a long time ago, which is we're going to produce some function called an embedding function, or we're going to use something called an embedding function, and the embedding function is going to take these tokens, so it's going to take one token at a time, and it's going to map a token to a vector. And the dimension of that space we'll use is d prime for now, because we're going to end up combining a bunch of these tokens or vectors together. Okay, so what the idea is going to be we're taking each token and we're mapping it to a d prime dimensional vector. And then we're going to concatenate all those vectors into one vector. Okay, this is called an embedding function. Okay, this is an embedding function. And for now, we're going to assume it's given. And we'll see later on what is really done in practice with this thing. But for now, assume it is given to you. So someone has come, and this is actually like very realistic. Like there's a lot of embedding kind of functions that have been learned in various ways online, and you can kind of just download them and use them and so on. Okay. And we'll talk about in a moment how to interpret tokens as vectors, what that would even mean. One very naive way to do this is to just represent each token as this one hot vector, which has only a 1 at the corresponding index, where that whatever token number that is. But that would require d prime to be as large as k. And that is often not used. But that's like the most simple way you could try doing embedding discrete things into vectors, is just embed them as these one hot vectors that are of dimension equal to number of tokens. Okay, and before we get into understanding this thing, let's just see how this would solve our problem. And the way it would work is now, this F probability thing really wanted a vector as input, right? Because that's being passed into the neural network. So how do we produce this vector? Well, it's going to be produced in the following way, which is you take the sequence of tokens, each one of them, you're going to map it through an embedding function, the same embedding function. That's going to produce an embedding vector. Each one of these guys is an RD prime. The number of them you're going to produce is the number of tokens in your input. Let's call that C for some reason. And then you're going to just concatenate all of these vectors. So you're going to concatenate and then add one bias vector, or one bias index. And then you get your input vector. Okay. So let me just make that a little bit more clear. So this thing is going to be called embedding bar. It's going to kind of take like the concatenation of all of them. And the way it works is that this E bar is going to take as input some sequence, which I guess will look something like V1 up to VC, right? And it will map it through the corresponding embedding functions and concatenate them. So it's going to like take the embedding function and pass through at V1, and then concatenation, I'm just going to use a comma to show that. So then it's going to concatenate with the embedding of V2 onto the embedding of VC, which is the number of tokens. And then you put that all into one giant vector, and then you add a bias, which is the one at the very beginning. Okay. So that's going to produce your new vector. And what is this? This is going to be equal to this x vector, which we wanted. And that is in R of D plus 1. Okay, so what is D? Well, D is going to be equal to the number of tokens times D prime, right? Because each one of these guys is in R of D prime. So each one of them is D prime dimensional. If you concatenate all of them, you get C times D prime. And then you get a plus 1 for the bias. So D is just C times D prime. And this kind of, okay, so that's what happens. And now there's one thing that's kind of annoying about this situation, which is that the kind of dimension really depended on the number of tokens. But of course, different inputs can have different lengths. And so the simplest way to address this is to say that our kind of, the way we're going to generate these tokens is we're just going to always assume the input is of some length. However, that's definitely not always going to be true, but we're going to just fix that problem in the kind of naive way, which will sort of work for most cases, which is if it's longer, we're going to just clip the beginning part of the input. And if it's not long enough, we're just going to pad the input. Okay, so this length is going to be called the context length, and this is just user defined. By user, I mean like you as the designer of the learner. You're going to just decide on this context length. You ideally want this as long as possible, but that will require you to do a lot more computation because this dimension will grow, right? It grows as C times D prime. And so, yeah, so that's going to be the idea. So we're going to always assume that the input has been kind of transformed to always have C length. And yeah, so if it's a longer sequence, you clip the input. And if it's shorter, so, okay, I can write this to handle, all right, let me write it like this. If a sequence is longer than C tokens, just take the last C tokens. Okay. And then in the, and then I guess I wrote this here. And then to handle sequences shorter than C tokens, this should be C tokens, you're going to just pad it at the beginning with this pad token. So you add a padding token at the beginning. So if you had a sequence of only 2 tokens, but your context length was 3, well, then you transform the sequence into pad token at the beginning and then the words afterwards. So this way you now have all inputs of equal length. Okay, and there's something I want to point out, which will also be discussed later on. This is not quite how the current language models deal with this. And in particular, the reason we're kind of running into this issue is because here, we really want to use a neural network of the same style as we've seen so far in this course. And that really did expect the input to be of it really expected the input x to be some D plus 1 dimensional vector. And there's really nothing we could do about that because you had to fix that kind of input dimension beforehand because that was being passed to these neurons, and it couldn't work with different input sizes. The current kind of neural networks that people use, which are these transformers, actually can kind of deal with different sized inputs. And so this is not quite how it's handled, but for the purpose of this, we're going to just deal with this current neural network style that we've seen, and I'll just make it as a note at the end that the current kind of language models can actually deal with these like different length sequences, kind of nicer. Okay. But the idea is sort of this, like all the ideas are the same in terms of this embedding function and so on. It's just this context length can actually be kind of variable. And the only reason there's like a real context length that ends up being used in practice for these models is largely due to the fact that computation would be really expensive over large contexts. And also, we'll see that the training data that's used is no longer than this context, so it probably would perform very badly on longer contexts. Okay, so it's more of like a practical issue than an actual theoretical issue of the architecture. Okay, so now let's study this embedding stuff. How do you think about these embeddings? So here's a way to think about it. So you can think about embeddings as somehow representing like semantics or the meaning of words in a vector space. Okay, so here's what I mean by that. So somehow we're mapping words into vectors. So the way we can understand what happens when you do this is you can see what words, like how do the vectors of different words look like and what are the relationships. So now I just tell you some properties of most embeddings that you would find online. Okay, so one property is that if you take some word, like for instance, the embedding of big, that's some vector, let's say, and we're using 2 dimensions because we can't visualize higher dimensions. What you would find is that if you look at the embedding for a synonym, such as the word large, let's say, so if you look, that's its embedding, what you'll find is that the vector representing these synonyms will likely be very, very close. So these points are very close to each other. That just seems to be a property that's observed. Okay. And then it turns out that relationships between like words also has a very nice kind of meaning. And so in particular, if like you looked at the word man, so this might be the embedding, it's just a vector in 2 dimensions. And then let's say the word woman had some other representation after mapping through the embedding. And maybe it's not that close to man, it's not a synonym, but like, I don't know, maybe it's over here for some reason. This is completely arbitrary that I chose it to be here. But what you can do is then you can be like, okay, suppose I then had another word such as like king. Okay, so far this example should have no idea where I'm going with this example quite yet. But now you might ask, okay, suppose I now wanted to find the embedding for queen, like the vector representation for the word queen, and you didn't know what it is. Well, it turns out that now you can do this kind of interesting, let's suppose king was here. You can do this interesting procedure, which is, like people will say that a woman is to a man somewhat like a queen is to a king. And so it turns out that if you took the actual vector difference between, let's say, man to woman, well, you could then take this difference, it turns out, and add it to the vector of king, and you will very likely end up with a point which is very close to the embedding of queen. And so moving along in this vector space, in terms of like these vectors and then moving along the relationships, have this very nice kind of meaning towards them. Okay. And so similarly, we can, and I just do another similar example to this. So like, there's, for instance, Rome is like the capital of Italy, and maybe Italy's embedding is over here. And so you can do a similar procedure to find, like, let's say the capital of another country. So suppose there was some other country, let's say France, that you were interested in, and its embedding maybe was over here for some reason. Well, then it turns out this kind of vector direction encoding capitalness or something like this can be captured by just checking what this vector difference was, and then taking that vector difference and adding it to France. And if you add that vector difference, what you'll find is that the vector you end up with should be very close to the embedding of Paris, which is the capital of France. Okay, and that's what you should kind of take away from these embeddings, is that somehow mapping discrete words, tokens, into vectors, if done correctly, can have all these like wonderful kind of relationships between them. Okay. And the nice thing is now we have vectors, which we have very used to using in this course. Okay. And now let's move on, which is kind of the last thing that's left. Is now we've done all this transformation to like the input and the output, and really we want to run ERM now on some data set. And the question is like, what does our data set look like? How do we get this data set? And that's really the last thing, because then after that, we will just really use ERM. And I'll tell you what the loss is and so on. And that is really how kind of these language models do end up being trained. Is there ERM is being run, well, in particular using gradient descent with a specific loss, which we've already covered in this course most of the time. And then there's all sorts of other like bells and whistles with the step sizes and the initializations and so on. But otherwise, the story is going to be follow exactly from what we've learned. Okay, and let me answer another question, which is someone asks, if we have a word we want to link to an existing set of words, can we embed both and calculate the cosine similarity to get the max? I don't know what the max part really means, but like, yes, if you embed a new word and then you add some other words, oh yes, so you can sure, you can do the like the cosine similarity between these two vectors, which is to kind of find the vector, the other vector that's the closest to it, and then that'll likely be a word that mapped to that vector that is very similar to the word you just embedded. That's true. Okay. Okay, and so let's just kind of move along so that I can get to a couple notes at the end that I wanted to. Yeah, okay, I think we're on track still. So last thing is just how do you create a data set? And the creation will look something like this. So think about like you have books on the internet, or you have a bunch of web pages and things like this. So that's a bunch of sequences of tokens. And roughly speaking, just take all these and put them into one giant sequence. So now you have like a sequence which is all the web pages kind of appended together and all the textbooks and so on and so on. And there are some details that why like there's some things that you would want to fix about this procedure, but for the purpose of this course, let's just go with this. So that's a giant sequence, and it's like there's going to be the first token in the sequence and the second and the third. And then eventually you're going to get to like whatever context length you pick, and that's going to be very early on. And then you go up to +1 and then keep going. And then let's say the length of this whole thing is going to be n + 1. And you'll see why I picked +1 instead of just n, so that it nicely maps to the normal terminology we've seen before. And then all you're going to do to create a data set is you're going to do the following, which is, okay, this is stuff on the internet, which let's say we take as kind of like our ground truth belief of how next tokens should occur in the world. Well, then if you took any like subsequence and you just took the next word or the next token, that is a perfectly good XY pair, which is like this would be your input and this would be your output that you should produce. And you could take some other subset and be like, oh, I want to produce this token in here. And so you end up taking every kind of like subsequence that's of length C, that's your context length, and then you just use the next token as the label Y. Okay, and so first we're going to break this up into sequences as inputs and Ys as outputs, and then we'll convert them into vectors in a moment. So it'll be like the first sequence would be something like S1 equal to just V1. And so now we're creating our data set. So this is like our first data point would be S1, Y1. And the reason I'm using S1 is because I'm going to map it to X as a vector in a moment. Okay, so this would just be V2. So it's going to be like, this is my input, and I want to predict double V2 here. So input, output should make sense, because that's how the data set says things should be. It says V2 should come after V1. Next data point is going to be V1, V2. And the label is going to be Y2, which is just V3. So you keep doing this until you get to S, let's say C, and at SC, what you'll have is V1 up to VC. So now you're at your max context length. And then YC is going to be just V of C plus 1. So that would be like when you get to here, that's your input, and you need to predict this. As you'll see, these are going to all get padded. Okay. And then afterwards, you end up just taking, so if you got up to here, you would take this as your input, and you would forget about this. You would just remove it, because that doesn't fit in your context. And then you would predict the next token here. And so anyways, if you continue this procedure, you get to the final one, which is SN, which is like V. Okay, there's going to be something up to, we know it's going to be up to Vn, let's say. And then Yn is going to be V of n plus 1. This is why we have V of n plus 1, because now you have Y1 up to Yn. And what is going to be here? Well, what's going to be here is that if you include Vn, well, you need to then only include the last C tokens, because that's your context length. So it will be n minus C plus 1. And you can see why the plus 1 needs to be there if you just do it on your own time. Okay. So that's how that's going to be broken up. And an example is like this. So if your context length is 2 and your entire sequence is just 3 words, 3 tokens for some reason, obviously this would be much larger if you took like the whole internet. This is how things would look like, which would be S1 would just be pad and the word Y. Okay, well here I didn't pad things, so let me do that. So it would be like, if you padded things, it would look like, okay, I need some more space. You would add a bunch of these pad tokens. And the number of pad tokens here would have been C minus 1, because then there's just 1 token here. And in this case, you would have had C minus 2 pad tokens. So C minus 2 of them. And then for the next ones, it is actually of the correct length. Okay. So yeah, in this example with just 3 input tokens, you would have a data set of 2 points, which is pad Y and then the word did. So from Y, you should predict did. And then your next data point would be Y did, and you should predict the word the. Someone asks, like, what if there are multiple of the same token or the same C tokens in S? How do we choose the next token? So I guess the question is something like, what if I run into some sequence here, which is like, Y did the, and then here it says chicken, and then later on it says, Y did the cat, or something like that. Which one is the correct prediction? Well, your model is going to learn that the one, if it happened like 50-50, then it'll probably learn to just predict with 50% cat and 50% chicken. If it ended up seeing chicken like 100 times and cat only once after that same sequence, it'll probably learn to predict chicken with much higher probability. And this should be thought of kind of similar to like, the previous classification things, which is if you saw some photo and maybe like 90% of people labeled it a cat, but 10% labeled it a dog. Well, then what you should learn is that the probability of this photo being a cat is 90% and 10% is a dog. And then your final prediction will just be the argmax of the 2 probabilities, which you would say, oh, it's a cat. Although behind the scenes, like, you're not certain, like 100% certain. Okay, and that's the same with language. And this happens a lot, of course. There's many sentences which have all sorts of different completions or next words, and your model will learn the probability of kind of each of them. And then what you will predict is the most likely one, let's say. Most probable one. We'll see how this is slightly different in the real language model world, though, in a second. Okay, and then finally what's left is to convert these to vectors. So the x, to get x1 to xn, you end up converting x1 as just, well, the embedding kind of concatenation function of S1. So you just pump this guy through the embedding concatenation function, and you get a vector in R of D. And you do this for all the x's, so you do this for x2 up to xn, and you end up with your inputs, your n inputs. These are all of these are in R of d plus 1. And your outputs will now, because you want to predict this k length probability vector, you need to put the class label through a one-hot vector map. So it'd be like y1 now becomes one hot, and this is just like converts it into a vector of k dimensions where it only has a 1 at class y1. This is one hot of the corresponding label y1. So this should be encoded as some number, right? And this word, though, would be encoded as another number in your vocabulary, and this would just give you a 1 in that index. So this is an element of 0 or 1, and it has 0 everywhere other than one of the indices. Okay, and then up to y of n. One hot y n s, yeah, this is also in 0 and 1. And of course, this is a subset of the continuous interval 0 to 1 to k, which is the probability vector you actually will end up predicting. And then ultimately, this gives you a data set, which is you group up x1, y1, as we've seen in this course many times. Well, yeah, these are actually vectors now, these y1s, because they're one-hot vectors, up to xn, yn. Okay, and this looks exactly like the multi-class classification setting now, which we have learned about. And so all you need to do now is just solve that problem. And we already know which function we're using, which is this like neural network style thing we saw above for predicting probabilities. And so ERM looks as follows. So it's like, okay, so now we have everything kind of set up. Now let's talk about the ERM algorithm and how it works with this, which is really how things end up being trained. So you take in this data set, which we have created, and this is like a whole pre-processing step to create this data set to look of the form that we've been studying in this course, and how basically all machine learning models end up working with data. Then, so we're going to predict a probability model, right? We're going to use that probability model in a moment to then predict next tokens. But first we predict, this is really like what the model does. Then there's going to be some like, kind of wrapper that picks the argmax. So you have this probability, and that's just going to be the minimum function in your function class, which we'll define in a moment, that minimizes the empirical risk. Everything as we've seen. Your function class is now going to be this function that maps input sequences, which are encoded as these big vectors, right, into giant probability vectors of k tokens. Each one of these functions is going to be the softmax applied to your neural network, which gives you a probability vector. The neural network is going to be some neural network with a fixed architecture that you choose beforehand. So then the only thing that changes between these neural networks is their set of weights. And what you're going to do is you're going to search over the set of weights. As we've talked about in this procedure, this argmin is just minimizing over the set of weights of your neural network, which we've seen how you do that with gradient descent and so on. So now you can see how this is exactly as we've seen in the neural network lecture with this neural network style of function class. Now, since we're doing this multi-class classification kind of thing with the labels, the natural loss to pick is this multi-class cross-entropy loss. And this is really what ends up being used in practice as well for the loss. The only difference is they'll add regularization as well, and use some other bells and kind of tricks and stuff that we've alluded to in the course based on our algorithms, like changing the initialization, changing the step sizes. Maybe you decay the step size, these kind of things. And all these kind of things get used. But at the heart of it, it's just this. Okay, and then ultimately, now you have this probability model. What you wanted to do is use it to predict new tokens, the next token. And the way that works is the following, which is, so to predict a new token, so for a new sequence, and this is really what happens behind the hood, which is like if you have a new sequence S, and you convert it to be length C. So if it's too long, you clip it, the input. If not, you pad it. So it's this sequence of length C, context length. Well, then the language model what it's going to do, or the language model is the following. It's going to be like, so this is our model. This is really what like these companies will produce at the very end of this whole ERM process. They'll do this, they'll get the probability model, and then they'll wrap the probability model into a language model. And the language model will work like this. They'll take in some sequence, which is your input, and they will select from, okay, so what you'll do is they'll run the probability model, right, through your input, S. How are they going to do that? Well, they're first going to take S and map it into a vector, right? They're going to map that through this embedding concatenation function. They map that into this vector, which we have seen. Then that is going to go through this probability model. That gives you a probability of each next token. And then the question is, well, which token do I pick? And one choice for this, I'm going to just call this y hat. This is a vector. Maybe I should call this y hat vector. And this y hat vector, you're just going to look through y hat. You're going to look through the indices q. Q is like the probability of token q, token number q. And you're just going to pick the argmax index. And q is a number between 1 to k. Okay. And that's really how you end up interacting with these kind of models, is that behind the scenes, there's this probability model that has been learned, and then there's this wrapper that chooses the next token. One way to do this is to pick the argmax. Okay. And now I guess I have 2 minutes to kind of wrap up on some notes. So finally, so the actual neural network architecture that gets used is a transformer, okay? Not this kind of multi-layer perceptron, which we've seen, just a different style. The embedding function is actually usually learned. So instead of having this like fixed embedding that someone's trained for you, it's actually learned simultaneously. So there's a set of weight vectors that themselves describe the embedding function that you will learn through gradient descent simultaneously. People don't actually use, for the vocabulary, they don't use words and punctuation and stuff. They'll actually break it up into characters. Sometimes this is very unusual, but instead their vocabulary will be like subwords. So there'll be chunks of words instead of like whole words. And that's because some chunks are somehow more useful or more commonly occurring. And then there'll be chunks with like sometimes a space added to it, and then things like this. So really the vocabulary is these weird subwords. And this way of choosing the subwords is called tokenization. And so the procedure to map like English characters or like sequences to these subwords is called using a tokenizer. Maybe I should put that. This is called like tokenization. And there's tokenizers that people will actually use from the internet. And so this most probable word, or the argmax, is not actually how people generate the next word. What they do is if you have this probability distribution of each word or token, they'll just sample from it. So if you have these like probabilities of these, just randomly sample from it. And so the word that has the most like highest probability will be sampled from most likely. But other times you might get more unlikely words. So you'll get some sort of like creativity from this model. So it's not always generating the same word every single time. So you can try prompting it with the same thing, and it will sometimes give you different things. Okay. And finally, the word large is for language models that have a lot of weights. And so for reference, like GPT-3, which is publicly available, we know that it had 175 billion weights, which is a lot. That's how many like of those edges there were. GPT-5 is like publicly estimated to be something like on the order of 2 trillion weights. And then finally, just for fun, maybe people like to say these kind of things, is like the human brain has something on the order of like 100 trillion weights, or like connections between neurons. So just to give you an estimate of like how we scale compared to maybe the human brain, which we're still, a decent ways off. And it's kind of fascinating because the brain is much smaller than the number of GPUs and stuff that these models are stored on. Okay, well, that's the end of this lecture, and I guess all the content for this class. So thank you.